Hey there, it's Shannon Myers, and today we'll be covering isomorphisms of graphs. This is really just the basics, but it's really interesting. All right, let's go. What we're going to do is start this one off with an example. So we're going to draw a graph G which has the vertex set v1, v2, v3, v4, and edge set e1, e2, e3, e4 in two different ways. So why don't we call them G and G prime? So G and G prime. And if we can do, you can put this stuff wherever you want. There's no one right answer. So for the first one, I'll do it kind of like this. So for G prime, let's do something like this. Let's say that we've got our V1 here, and let's call this one V3, and then V2 can be here, and V4, something like this. So I basically just switched vertices V2 and V3, and now for the edges, we'll do them in a different color in blue. What if I had edge 1 here, and I have edge 2 here now, and then edge 3 up top, and edge 4 along the bottom. All right, so let's take a look at the very bottom, right, where I have these different sets. So, I've got E1, E2, E3, and E4 from G prime. I've got E1, E2, E3, and E4 from G. And then the V1, V2, V3, and V4 from G. And then I'm keeping the colors matched up, V1, V2, V3, and V4 from G prime. And let's see if we can see if there's any kind of correspondence between these, right? And there's more than one way to do these things, of course. But here, one real easy way to see is when I constructed my graph, do you see that I switched the vertices? So if I go vertex to vertex and take a look at this, V1 is still in the same spot, right, in both graphs, right? So in G, V1 maps to V1 of G prime, but V2 in G maps to V3 in G prime. That makes sense? And then what? What do you think? And there's, like I said, more than one way to do this. V3 in G would map to V2 in G prime, and then V4 in G maps to V4 in G prime. Now, let's take a look at how the edges would then correspond. Well, edge 1 in G would correspond to edge 3 in G prime, right? Edge 2 in G would correspond to edge 2 in G prime. And then edge 3 in G would correspond to edge 4 in G prime. And edge 4 in G would correspond to edge 1 in G prime. And again, there's more than one way to do this. And this one, there was multiple ways because the degree of each vertex was the same. They all had a degree of 2. And remember, that's because there's the number of edges that are incident on each vertex is the degree. So here we go. So we've got this going on. So it turns out that some graph G is isomorphic to some graph G prime if and only if the vertices and edges of G and G prime can be matched up by 1-to-1 onto functions such that the edges between corresponding vertices correspond to each other. Okay? Note that a function f from some set x to another set y is onto if and only if, given any element y in the set y, it's possible to find an element x in the set x with the property, that capital F at x is equal to y. Or maybe I should really write it the other way. Y is equal to capital F at x. So what that means is that if you've got some pre-image x, right? Some pre-image x, that every element in the set y has to have a pre-image, has to have some input. Okay? So you'll learn more about that in linear algebra. So now let's take a look here. I mean, would you say that these are 1-to-1? I mean, if you remember, there's for a relation to be 1-to-1, every input has exactly one output that is not repeated, right? In basic words. So y equals x squared. That function is not a 1-to-1 function because it doesn't pass the horizontal line test, right? So here, notice that each input has exactly one output, and that output is not repeated for any of the other inputs. So, looking at this, I would say it's 1-to-1. There is an input for every output, right? And it works for both the edges and the vertices, right? Both those correspondences. So here, I mean, we could call this one some correspondence G. This could be some correspondence H. And then we get to the actual, official definition. So let G and G prime be graphs with vertex sets V at G and V at G prime and edge sets E at G and E at G prime respectively. It turns out that G is isomorphic to G prime if and only if there exist 1-to-1 correspondences G such that V at G maps to V at G prime and H such that E at G maps to E at G prime, that preserve the edge endpoint functions of G and G prime in the sense that for all V and V at G and E and that belongs to E at G, V is an endpoint of E if and only if G at V is an endpoint of H at E. Okay, so basically, what do we have going on with these two graphs, right? If you look at what edges are between which vertices, right? Do you see that if we made sort of a chart of G and G prime, right? And we looked at, in G we had V1, E1, V2. At G prime, what did we have? I mean, what are we supposed to be looking at? Well, wouldn't it be V1, E3, V3? And that is why we said that V1 mapped to V1, but we said that V2 mapped to V3. And we need to make sure that the edge relationship is preserved. And so, do you notice that in the second one in H, that E1 maps to E3? So we're all good to go there. All right, so continuing, we have V2, E2, V3. And in G prime, what would we have? We'd have V3, E2, V2. So if V2 maps to V3, we're good on that. And V3 would have to map to V2. And notice that we did that on our chart down here. And so it's preserving the edge endpoint function. And then continuing, V3, E3, V4, right, for graph G. And for graph G prime, what do we have? We have V2, E4, V4. So notice that, again, we have that relationship that vertex 3 maps to V2 down in our correspondence G. And then we have that V4 maps to V4 in that same correspondence. And so we want to make sure that the edge relationship is still there. And so here we would need edge 3 to correspond to edge 4, and we have that. And for our very last one, in the graph G, we'd have V4, E4, V1. And in G prime, that would be what? V4, E1, V1. And so we already have vertex 1 mapping to vertex 1 and vertex 4 mapping to vertex 4 in the correspondence G down here. And in the correspondence H for the edges, we would need what? We would need, beautiful, E4 and G to correspond to E1 and G prime. So that's what it means for the edge endpoint function to be preserved. That's what that means. All right, so let's look at a theorem, and the proof is in the text. I'm going to spend the time on examples. So graph isomorphism, it turns out, is an equivalence relation. So if we let S be a set of graphs and let R be the relation of graph isomorphism on S, then R is an equivalence relation on the set S. So for theorem 10.4.2, if you needed this for the final, I would provide this. A property P is called an invariant for graph isomorphism if and only if, given any graphs G and G prime, if G has property P and G prime is isomorphic to G, then G prime has property P. That part is actually a definition. And so the theorem states that each of the following properties is an invariant for graph isomorphism where M, N, and K are all non-negative integers. So long story short, if graph G has one of these properties, then in order for it to be isomorphic to G prime, then the graph G prime has to have this property. So both of them have to have N vertices, same number of vertices. They need to have the same number of edges. You'd have to have a vertex of degree K, and this will make sense when we do the next example. Have M vertices of degree K, has a circuit of length K, and we covered circuits last time. A circuit is a closed walk that contains at least one edge. Has a simple circuit of length K. So a simple circuit is a circuit that doesn't have any repeating vertices except for the first and last. Has M simple circuits of length K. is connected has an Euler circuit, and has a Hamilton circuit. So these are just special circuits. A Euler circuit is a circuit that contains every vertex and every edge of the original graph G, and a Hamilton circuit is a simple circuit that includes every vertex of G. All right. So now let's get to another example. So example 2, we want to determine whether the graphs of G and G prime are isomorphic. If they are, give functions G and H that define the isomorphism. If they're not, give an invariant for graph isomorphism that they do not share. So let's check this one out. So what I'm going to look at first is this. Do they have the same number of vertices, and do they have the same number of edges? So in graph G, there are what? 4 vertices, right? And in graph G prime, there are, good, 4 vertices. So that checks out. And then how many edges in the first graph G? Beautiful, 6 edges. And 6 edges in G prime. So far, we're good, right? Then you can look at the degree of the vertices. And really with this, it's something that will help you figure out the correspondence anyway, so it's good to do up front. Really, what I do with these is I make sure that the number of vertices is the same in G and G prime, the number of edges is the same, and the degree of each vertex, or of the, there's a degree matchup in the vertices, and that way the degree of the graphs are the same, and we can find which vertices are that correspond to each other. So here we go. So the degree of vertex 1 is equal to what? How many edges are coming out from it? And we're working on graph G. Beautiful. 2. The degree of V2 is what? Yeah, be careful. It's going to be 4, isn't it? Because you count a loop twice, right? So it's got 2 edges coming out, and then you count the E2 twice, so you get a degree of 4. And the degree of V3 is going to be, good, 4. There's 4 edges coming out from it. And the degree of V4 is, beautiful, 2. So let's check G prime, okay? So the degree for W1 is equal to, perfect, 4. You see that loop that it has? So it's got 2 edges, F1 and F5 from it, and then it's got F6 as a loop. So that degree is 4. The degree of W2 is, let's see, we've got F1 comes out, F2 comes out, F4 comes out, and F3 comes out. So we have 4. The degree of W3 is just 2, right? And then the degree of W4 is also 2. Cool so far? So on this one, the degree of the graph G is 12. And this one, if you add it up, you get 12 as well. So the degree of the graph G prime is also 12. So that's good. And we get an idea of, which vertices will correspond to each other, because as you can see, these graphs are very different in look. So, all right, let's do our correspondence. So here, if we have our So we have our vertices of G. We have vertices of G prime. We're going to see if there's some kind of correspondence. Sorry, it's so hard to get ovals to look alike. So the first ones are what? V's, V1, V2, V3, and V4. And then G prime has W's, W1, W2, W3, and W4. Now, let's go ahead and set up for the edges. So the edges of G, the edges of G prime. And if we can't, if we can't do it, then we can't do it. That's fine. So the first one has E's, E1, E2, E3, E4, E5, and E6. And then the second one has F's. So F1, F2, F3, F4, F5, and F6. So, like I said, it's a little bit more complicated. So let's do a table kind of like we did before. And what we're going to do is we're going to look at the ones, we're going to start working on the correspondences. So here, if we take a look at, G and G prime, and what I'm looking at are, edges that are between angles, okay? Or I'm sorry, edges that are between vertices. So in G, what do we have? I'm going to just start with V1 and V2, right? So we've got, I guess I'll do some different colors so it's easier to see. So in G, we have V1, E1, V2, right? Now, what was the degree of V1? Beautiful, it was 2. What about the degree of V2? It was 4, right? So here, I need to have, for the first one, something that is of degree 2, and the second vertex has to have degree 4, right? And then, so that's why there's more than one isomorphism, because, more than one, there could be more than one correspondence that works. So, what is, I'll go ahead and I'm going to put all of these short walks of G and go from there. So we have V2, E2, V2. We have V2, E3, V3. We have V3, E4, V4, and these are all in G. We have V4, E5, V3, and then we have V3, E6, V1. Sorry about the dog. And I think we're done. All right. That makes 1, 2, 3, 4, 5, 6 edge things. All right. So now in G prime, what do we have going on? In G prime, what's going to happen? So remember, we want them to correspond. So I'm going to look for, just for ease, I'm going to look for the loop right? And see if I can make that one work. So do you see that W1 has a loop, right? And that one had degree 4. So if I put W1 here at the end, then I am potentially matching it, corresponding it to V2. And then, so I need to figure out what's going to correspond to V1, right? So here, if I take a look at W3, W3 has a degree of 2, right? Because it has edges F2 and F5 coming out from it. And the only other option could have been W2, but W2 has a degree of 4, so it won't, each vertex has to have the same degree. So I think we found our match. So W3. Well, what edge is going from W3 to W1? Awesome. Edge F5. Cool so far? So we're thinking that V1 corresponds to W3. Cool so far? All right. And what other ones did we think were corresponding? Perfect. V2 would map to W1. And we'll see if that'll hold. And while we're at it, we're saying that E1, edge E1, maps to F5. Okay, so here we go. We would have to have W1 start, right? Because that's the one we're saying corresponds to V2. So can we keep this going on? Well, remember, W1 has a loop, so we'll have W1, F6, W1. So we're good there, and that gives us the information that what? We already have the vertex correspondence. This would make the edge correspondence, E2 would correspond to F6. Does that make sense? Awesome. All right, so now, again, we have V2 mapping to, W1. So we're still good there. And now V3, we haven't figured out yet, right? So V3 is the other one with degree 4. Well, there's only one other vertex in G prime that has a degree of 4, and that was W2. So I'm going to say that it would have to be W2. V3 would have to map to W2. So let's see if it works, right? Well, in our original graph of G, we have our edge 3 in between V2 and V3. So in between the vertices of degree 4 was edge 3. Well, in between the vertices of degree that both have degree 4, which are W1 and W2 and G prime, what do we have? We have F1. Beautiful. So that would mean an edge correspondence of E3 mapping to F1. Groovy? Okay, continuing. Now we've got that V3 maps to W2, right? Well, what's left? I mean, V4 would have to map to W4, right? And so let's see if that's going to work. So V3 and V4, so V3 has a degree of 4 and V4 has a degree of 2, right? So let's take a look. There's, a couple of different situations. So we had said V3, E4, V4. So we're going from the one with degree of 4 to the one with degree of 2. So we need the edge in between that for graph G prime. So here we go. The W2 to W4 is going from degree 4 to degree 2, and I think it'll be F3 that's in between them. So E4 would have to correspond to F3. So far so good for isomorphism. So now looking at V4, E5, V3 in the graph of G, V4, E5, V3. Now we're going from the vertex that has degree 2, V4 has degree 2, and V3 has degree 4. So if we did W4 to W2, that would keep that correspondence. And so then the edge that they share, that's in between them, is F4. And this was, and then it went to W2. Cool so far? So now we have a correspondence between edge 5, E5 rather, and F4. Okay, so just one more left. If edge E6 corresponds to F2, we're good to go. So now we're going from W2, and then V1, remember, corresponded to W3. So when I look at W2 and I go to W3, F2 is in between those. And yes, that means that we've got the correspondence. So if we call this one G and we call this one H, whoops, we have our functions G and H that define the isomorphism. So these are the functions G and H that define the isomorphism, and you can just give your results like this. Cool, cool? All right. Definition. So if G and G prime are simple graphs, then G is isomorphic to G prime if and only if there exists a one-to-one correspondence G from the vertex set via G of G to the vertex set via G prime of G prime that preserves the edge endpoint functions of G and G prime in the sense that for all vertices U and V of G, if you've got the set UV is an edge in G, then if and only if G at U, G at V is an edge in G prime. Okay, so again, let's show this definition by using an example. So for each pair of simple graphs G and G prime, please determine whether G and G prime are isomorphic. All right. So if they are, we want to give a function G that defines the isomorphism. If they are not, give an invariant for graph isomorphism that they don't share. So that's from that other theorem, which you don't have to memorize. So again, let's take a look at the degree of each of these graphs, G and G prime. So we look at the degree of each vertex. So the degree of A is 2 because there's 2 edges coming from it. The degree of B is also 2. The degree of C is 3. The degree of D is 2. The degree of E is 2. And the degree of F is 3. So coming over here, let's look at the total degree of G. If you add up all these degrees, you'd have our degree of G will equal to 4 plus 11, 14, right? Is what they sum to. Okay, so now let's look over here. So the degree of U is equal to 2. The degree of V is equal to 2. The degree of W is equal to 2. the degree of x is equal to 2. The degree, of y is equal to 3. And the degree of z is also equal to 3. So this one will have the same, it'll sum to 14, so the degree of g prime equals 14. So now let's take, and they each have, 6 vertices, right, and 7 edges. So 6 vertices, 7 edges in G, and 6 vertices and 7 edges in G prime. All right, well, let's just go ahead and try to make our function. So this one's a little bit easier because since these are simple graphs, we don't have to, go through as much as we did before in order to, we don't have to do both an edge correspondence and a vertex correspondence, just the vertex correspondence. So let's do it. So our correspondence G then would be, if it works, so since we're only doing the vertex correspondence, we just need to draw it once. So we've got our A, B, C, D, E, and F from G. And we have U, V, W, X, Y, and Z from G prime. So now let's see about the correspondence. So A has a degree of 2. And so we need to, figure out which ones can correspond to other ones. So A has a degree of 2 and U has a degree of 2. So potentially A could correspond to U. B has a degree of 2 and V has a degree of 2. So I'm thinking those might work out. And then what about C? C has a degree of 3. W's got a degree of 2, so we'll definitely have to figure out some other situation here. So I'm thinking that C could correspond to Y because Y also has a degree of 3. And then D's got a degree of 2, so we could have D correspond to W. E and X both have degree of 2, and then F and Z both have degree of 3. Now the reason that we don't have to do the edge correspondence in here is because a simple graph, it doesn't have any loops or parallel edges. So you're not going to have as much trickiness as we had with the other ones. The previous example had parallel edges going on. Remember, like F3 and F4 are parallel edges, as are E4 and E5 in the graph of G. So with the simple graph, there's less to check. So this here would be the result, the isomorphism that you'd be looking for. Cool? Okay, so, and you can put it in that format on the exam. Now, let's take a look at the next problem, number 2. So for number 2, well, what do you think? Is there another way I could draw the graph of G? Yeah, I mean, couldn't I do like, for the graph of G, it could also be drawn, so you could have your F, your B, and your D, like that. And then remember that there's over here where they connect, right? There's no vertices. So you don't have to draw the graph of G like that. You can actually take it apart and you can say, oh, here I've got my A, my C, and my E, and we can draw it like this. And so the graph of G is not connected. So G is not connected. And if you look at 10.4, right, what does it say? In one of the invariants, in variance, do you see that it has to be connected, right? G is not isomorphic to G prime, since G is not connected. Cool, cool? All right. So that wraps up 10.4, and I hope you enjoyed the show, and I hope you have a wonderful morning, afternoon, or evening whenever you're watching this clip. And if you like what I'm doing, please subscribe. Bye.